So from this lecture, we'll start with the introduction of dipoles. So what are dipoles? How do dipoles behave? So you already learned the basics in classes. Okay, dipoles are nothing but positive charges and negative charges separated by distance 12. The dipole moment is given by q into 12. So those things we learned in the class. We learned about the advanced topic or the advanced concepts regarding dipoles out here. Okay, in these lectures. From this lecture onwards, we'll start with the concept of dipole. Okay, so dipole is nothing but a positive charge and negative charge of equal magnitude separated by some distance. Okay, in some books that distance is taken as L, in other books that distance is taken as 12. Okay, dipole is a vector quantity and the vector goes from the direction of negative charge to positive charge, and the magnitude of dipole is given by q. Q is nothing but charge on this positive charge or charge on this negative charge. Both these charges are of equal magnitude. Okay, they are separated by a fixed distance L into the distance between dipole or distance between positive charge and negative charge. So whenever I'm saying dipole from now on, I won't be showing this positive charge or negative charge. I'll just be showing this dipole as a vector quantity. So you have to imagine a positive charge at the arrowhead and a negative charge at the tail of the arrow. Okay. Now inside your syllabus, okay, there are two aspects of dipole that you have to remember or learn. The first one is electric field created due to a dipole. Okay, see, while studying charges is to create an electric field. Okay, and suppose someone created an external electric field, charges is to also behave inside an electric field. No, the same thing you have to learn out here. Okay, how does a dipole create an electric field? That's the first concept that you have to learn. And the second concept is an external electric field is already created. How does a dipole behave inside this electric field? Okay, so these are the two fundamental concepts you have to learn out here. Same as charges. In charges, what did you learn? There was external electric field. How do or what was the force acting on the charges, or what is the acceleration of the charges? That was the second concept, and the first concept was is a combination of charges. What is the electric field out here, or what is the electric field out here? Isn't it? So these two fundamentals will learn also in dipole. Okay, in dipole, instead of addressing the charges separately, we'll address the dipole moment or dipole moment as q into 12 or q into charges between the dipole, charges between the positive charge and negative charge. Okay, now the first thing that you have to learn is electric field at axial position. Okay, axial position. What I mean by that is, see, where is axial position? Axial position is nothing but along the axis, along this axis. Okay, now suppose I want to find out electric field at this point along the axis. Okay, this is the axis of the dipole. The electric field along the axis would be E axial is equals to 2 kp by r cube, where r is nothing but the distance of the dipole from the point. Okay, understood? So if I draw in this diagram, it would be nothing but this is axial position. Okay, I have to find out the electric field at axial position at distance r. Okay, where E is equals to minus 2 kp by r cube. Now two things you have to notice out here. The first thing is uh, this r is the distance between the point and the center of the dipole. This r is not, neither from positive charge nor from negative charge. It is from the center of the dipole to this point where electric field is to be calculated. This is the first thing you have to observe. Understood? K is nothing but 1 by 4 pi epsilon naught. P is nothing but q into 12. The second thing you have to remember is the direction of electric field in axial position will always be along the dipole. Okay, E axial. That means E axial will be 2 kp by r cube in this direction. It doesn't matter you keep the or you find out the electric field out here or electric field out here. Direction of electric field will always be along the direction of dipole. Out here also electric field will be in this direction. Okay, the derivation is also already done in your classes. Then also I'll show you briefly the derivation of dipole moment at axial position. Okay, it is nothing but simply see at axial position. Okay, electric field due to positive charge would be in this direction. Okay, it would be kq by this distance. This distance is nothing but r minus l whole square minus or this negative charge. The electric field would be in this direction. So minus kq by r plus l. That means this entire distance r plus l whole square. Okay. Now when you simplify this equation, you get 2 kpr by r minus l whole square. Now the important assumption that is taken out here is that the distance between the charges is very small when I'm comparing it to the distance where I'm finding out the electric field. That means this 2L, okay, is very small when compared to this R. Understood? So out here in this equation, I'll take L is tending to 0 and it would be 2 kp by RQ. Okay. Now the second portion of the syllabus is dipole or electric field due to a dipole at equatorial position. So equatorial position. Okay, so this is the dipole. This already is done inside the class. I'm just skimming it over, that's why. Okay, a dipole moment of P. I have to find out the electric field at distance this. Okay, a distance r from the equator of the dipole. This is r. Always remember the electric field would be opposite to the direction of dipole, and the magnitude of electric field due to dipole is nothing but kp by r cube. Okay, I'll just briefly do the derivation out there. Okay, so out here what we have done is to find out the electric field out here. So electric field due to this positive charge would be along this line. Electric field due to the negative charge would be along this line, isn't it? Okay, now see, the y component of electric field out here would get cancelled. The only thing remaining would be electric field along the x component or along this line. So if I make this angle theta, this angle is also theta. So the total electric field along this direction would be E cos theta plus this electric field cos theta. Now due to the symmetry, this charge is also Q, this charge is also Q. That's why this magnitude will be equals to this magnitude. So the total electric field along this direction would be 2 into E cos theta. So 2 into KQ by R square L square, 2 into KQ by R square plus L square into cos theta. Now what is cos theta? Cos theta is nothing but base by hypotenuse. Base is nothing but L. Hypotenuse is nothing but under root of L square plus R square. Pythagoras theorem. Okay. And when I simplify this thing, it would come as Kp by R square plus L square to the power 3 by 2. Now if I apply the same approximation means L is tending to 0, I'll get the answer Kp by Rq. Okay. So electric field at equatorial position would be Kp by Rq. Okay. So you have already learned that if a dipole is there, okay, the electric field at equatorial position would be Kp by R cube, and the electric field at axial position would be 2 Kp by R cube. 2 Kp by R cube, isn't it? Where R is the distance calculated from the center of the dipole. This is distance R for this equatorial position, and this is distance R for the axial position. Now my question is, or the question that is given out here is, if a dipole exists like that, okay, what is the electric field at point S? See, whenever such questions exist, we have to find the electric field due to a dipole, okay, at arbitrary position, not equatorial or not axial. So what you have to do out here is, you have to component the dipole, see, into two perpendicular dipoles. The first dipole would be perpendicular to the r vector, isn't it? So you can find out the electric field due to this dipole, and the second dipole would be the axial dipole vector. Okay, understood? That means this dipole is component into this and this perpendicular dipoles. The angle between the perpendicular dipoles is nothing but 90 degree. Okay, so if this angle is theta, okay, this angle is theta, okay, so this angle is nothing but 90 minus theta or theta dash. I'm computing this dipole P along this line. So the component of dipole along this line would be P cos theta dash, or P cos 90 minus theta, or which is equals to P sin theta. P sin theta. Similarly, component of this dipole along this axial line would be nothing but p cos theta, isn't it? Because this angle is theta. Now you got two dipoles. For the first dipole, I have to find out the electric field at axial position at distance r. So what is the electric field at axial position due to distance r? 2k. What is the value of dipole? See, p was nothing but dipole, no? What is the value of dipole? P cos theta. You have to find out the axial position due to this dipole, no? So 2k p cos theta by r cube, and there would be one more electric field generated due to this dipole, where is p sine theta, isn't it? And p sine theta generates a dipole at, or generates an electric field at equatorial position. The direction of p or electric field out here due to p sine theta would be in this direction, isn't it? And the value is kp by r cube. So it would be nothing but k. What is the value of dipole out here? P sine theta by r cube. P sine theta by r cube. Okay. So electric field due to any dipole is nothing but kp cos theta r cube in axial direction and kp sin theta r cube in equatorial direction. Understood? So now what you are going to study is about the potential due to dipole at any point. Okay. So this was dipole. This was a dipole P. Okay. Now at distance r at angle theta, I want to find out the potential at this point. Okay. And to find out the potential at this point. Understood? And if I say the electric field perpendicular to r is nothing but kp sin theta by r cube, and electric field along r is nothing but 2kp cos theta by r cube. Fair and fine. Now imagine this length to be infinite. Okay. Now if I'm moving a positive charge along this line, okay, a positive 1 coulomb along this line, the work done by this electric field is equals to 0, no? Because electric field is in this direction, I'm moving the particle along this direction. So the angle between force and displacement is always 90 degree. So the work done by electric field due to this electric field, okay, is equals to 0. Understood? So the potential developed due to this electric field is equals to 0. Which force would be doing some work? This component of force would be doing some work if I move a charge along this line, isn't it? So can I say work done, which is nothing but minus dV, or work done on 1 coulomb, is equals to force on 1 coulomb dot dr, isn't it? Now see, this potential would only be developed due to this electric field, because this electric field does zero amount of work, isn't it? So if I solve this one, minus dV is equals to, what is the value of E? 2kp cos theta by r cube, okay, into dr. Understood why I didn't take this component of electric field? Because work done by this component of electric field is equals to 0 when I'm moving a positive 1 coulomb along this line. Fair and fine. Now if I solve this one, minus v is equals to 2kp cos theta dr by r cube is nothing but r to the power minus 3 plus 1 by minus 3 plus 1. I'm just integrating those things. Okay. R to the power minus 3 plus 1 is nothing but minus 2. Minus 2. Out here also minus 3 plus 1 is nothing but minus 2. Now can I bring this constant minus 2 outside? Of course. This 2 would get cancelled. This plus would get cancelled. Sorry, this minus would get cancelled. So equation becomes potential is equals to kp cos theta r to the power minus 2. Now, r to the power minus 2 can be written as 1 by r square, isn't it? Now the important part of the equation, or the limits of the integral. Okay, if along this line, okay, along this line, where is the datum point? See, datum point is at infinity, no? At infinity, potential is equals to 0. And as I bring to this distance r, I have to find out the potential at this distance r. So at infinity, at r is equals to infinity, potential is equals to 0. at a point r is equals to r, potential is equals to v. Or I can easily say v minus 0 is equals to kp cos theta divided by r square, or you can write this as kp cos theta 1 by r square minus 1 by infinity square. 1 by infinity square is a very large number, so it becomes potential at any point r is equals to kp cos theta by r square. Okay, now you can check the points. Potential at this point, okay, cos theta becomes 180. Okay, 180 is minus 1, so potential at near the negative charge would be negative, potential at near the positive charge would be positive. At this line, potential is equals to cos 0. Cos 0 is nothing but 1, so kp by r square. Understood? At the middle point, or at the equatorial position, cos theta is equals to 90, so potential at equatorial position would be 0. Understood? Now what I'll try to do is I'll try to derive the same formula using another method, and this method is very important for the upcoming problem. Okay, so there is a dipole p, and we have to find out. Oh, let me draw this bigger, okay, because you won't be understanding the geometry if I draw it smaller. This is a dipole, and you have to find out the potential at distance r. Okay, potential at this point at distance r, making an angle theta with the dipole. What is dipole? Dipole is nothing but charge into distance between them. So let's say here it was positive charge q, here it was negative charge q. Okay, and the distance between them was 2l, l, l. Fair and fine. Now potential at this point is nothing but kq by this distance minus kq by this distance, isn't it? Okay, so we have to find out this distance and this distance. Okay, now there's a very important assumption that you have to take out here. The assumption is this l, or this length, is very small when compared to this length r. Okay, that means the length between the dipole is very small when compared to this length r. So how do you take this kind of assumption? See out here, we draw a perpendicular line out here, okay, and out here. Fair and fine. Okay, okay. So if I say this angle is theta, okay, this angle can also be said as theta, no? See, although by geometry I know these two lines are not parallel, okay, but the thing that we have to see out here is this arc or this point is very far away. That means they are converging after a very long distance. That means for a certain time they are parallel, no? After a while they will go and converge up to means out here, okay. So for a certain distance they should be parallel. They can be taken as parallel. So if this is theta, this is nearly equals to theta. Okay, it should be lesser than theta, but nearly. This is suppose 90 degree. This should be 89.99 because the length of this is very small when compared to this r. Understood? See, what I'm trying to say is, suppose a very small length is there and a very large length r is there. Okay, now if I draw these two lines, see, even though these two lines are meeting, isn't it? Can I say these lines and these lines are parallel for a little bit while? So if I say this angle to be theta, this angle is also theta, no? Although I know the bottom angle is little bit lesser than theta, but I can approximate them as equal. The same thing is happening out here. If this angle is theta, this angle is also theta. If this angle is 90, this angle is 90, and this angle is also 90. Understood? Now the problem becomes very simple. Potential is equals to, or potential due to this charge is equals to kq by this distance. Now what is this distance? R minus this much distance, and this much distance is nothing but L cos theta. So this is nothing but L cos theta, and this much distance is also but L cos theta. Okay, this much distance is L cos theta. See, L cos theta, and this much distance is also L cos theta. L cos theta. So this distance would be nothing but R minus L cos theta. So R minus L cos theta, and this distance, okay, this entire long distance is nothing but R plus L cos theta. So this entire long distance is nothing but R plus L cos theta. And now we have solved our problem. See, potential due to this positive charge is nothing but kq by distance between them, R minus L cos theta. Okay, minus potential due to the negative charge, kq by R plus L cos theta. Now when you take R common, or sorry, kq common, kq, okay, 1 by R minus L cos theta minus 1 by R plus L cos theta, isn't it? Now if I just simplify this term, I'm just simplifying this term, it is nothing but R plus L cos theta minus R plus L cos theta, okay, or see, R minus L cos theta bracket. That means this term minus this term divided by how much? Put the term R minus L cos theta into R plus L cos theta. I'm just doing it quickly, okay? Cos theta. See, out here R and R would get cancelled. Minus and minus would become plus. So L cos theta plus L cos theta is nothing but 2L cos theta, or is equals to 2L cos theta divided by A minus B into A plus B. It is nothing but A square minus B square. Okay, so this is nothing but R square minus L square cos square theta into KQ, isn't it? This KQ should be multiplied, no? KQ should be multiplied, or KQ should be multiplied, or V is equals to KQ. Now what is Q into 2L? Q into 2L is nothing but the dipole, or potential at point R is equals to Kp cos theta by R square minus L square cos theta, cos square theta. Now you already know, okay, R is much greater than L, okay, R is much greater than L. Therefore, L square cos square theta is very small when compared to R square, isn't it? So this component or this function will be 0. So V is equals to Kp cos theta divided by R square minus L square cos square theta. And since R is much greater than L, this tends to 0, or V is equals to Kp cos theta divided by R square. This is the same formula of potential that we have obtained before. Okay. And this is one of the method. The previous one was also one of the method. So whichever you like. But this method will come handy in the upcoming problems. Okay, we'll see how. Now I'll use the same method to find out the electric field at point S. Okay. That means this is a dipole. Out here a positive charge is there. Out here a negative charge is there. Okay. Q positive charge and Q negative charge. The distance between the dipole is 2L, isn't it? Out here point S is there, and this is distance R. Okay, from the positive charge, this is nothing but R minus L cos theta, and this distance is nothing but R plus L cos theta, R plus L cos theta. And due to positive charge, the electric field would be in this direction or along this line. Okay, electric field due to positive charge, and due to negative charge, the electric field will be along this line. Electric field is along this line, E due to negative charge. Now one of the assumption was this R is very large compared to this distance L. So that means this angle is tending to 0, no? So if this angle is tending to 0, can I say that E plus Q and E minus Q are collinear? Okay. See, what you have to imagine out here is as I go further and further away, this angle decreases and decreases. up to a point where this angle tends to 0, and when this angle tends to 0, this electric field and this electric field can be assumed as collinear, no? Okay, so if I assume that point, the total electric field at point S is equals to electric field due to plus Q minus electric field due to minus Q. What is the electric field due to plus Q by Coulomb's law? KQ by R square. What is the value of R? R minus L by, or R minus L cos theta. R minus L cos theta whole square. What is the value of minus Q? KQ by R plus L cos theta whole square. Okay, or electric field is equals to KQ by R minus L cos theta whole square minus KQ by R plus L cos theta whole square. Now from these two terms I can take KQ common. So if I take KQ common and put it outside, it will become 1, 1 and KQ. If I take the LCM out here, it will be R minus L by L cos theta whole square into R plus L cos theta whole square. So out here I'm just multiplying this term, and what would come out here in the numerator? This would become this term minus of this term, isn't it? So R plus L cos theta whole square minus R minus L cos theta whole square. Fair and fine, isn't it? Now look properly. Okay. Now if I do this term, okay, if I expand this term and expand this term would get cancelled with this term. This term would get cancelled with this term. See, a plus b whole square is nothing but a square plus b square plus 2ab. So this term will have r square plus l square cos square theta plus 2rl cos theta, isn't it? And this term would be how much? R square plus L square minus 2rl cos theta, isn't it? Now if I see this term minus is applied to this term, no? So everything out here would be multiplied by minus 1. So this r square and this r square would get cancelled. This L square cos square theta and this L square cos square theta. See, I've written a little bit wrong out here. It should be r square plus L square cos square theta. R square plus L square cos square theta. Okay. R square plus L square cos square theta minus 2rl cos theta. A square plus b square minus 2ab. So this r square and this r square will get cancelled. This L square cos square theta and this L square cos square theta will get cancelled. Okay. However, this 2rl cos theta and minus becomes plus. So 2rl cos theta and 2rl cos theta would become 4rl cos theta out here. So the numerator would become 4rl cos theta. Okay, 4rl cos theta. Okay, so let me erase everything else. Fair and fine. So electric field at point S is equals to KQ4RL cos theta divided by, this is nothing but A minus B whole square into A plus B whole square. Okay, or it is nothing but A minus B into A plus B 2 times, no? So this is nothing but R square minus L square cos square theta whole square, isn't it? See, A plus B into A minus B whole square. This can be written as, understood? So if I see KQ into 4L, okay, this can be written as E is equals to 2K into Q into 2L into R cos theta. I just rearrange these terms. Okay, 4 is divided into 2 into 2. One of the two I wrote outside and the other two outside. KQ RL cos theta divided by R square minus L square cos square, or cos square theta whole square. Okay, now Q into 2L is nothing but dipole P. P out here was nothing but q into 2l, or charge into distance between the dipole. Okay, so the electric field at point A would become 2k p r cos theta, okay, divided by r square minus l square cos square theta whole square. Now assuming r is much greater than l, this entire term would become 0, isn't it? Or E is equals to 2k p r cos theta divided by r square whole square, or r to the power 4. Now this r and this r would get cancelled to become cube. So this is nothing but r by r cube. Okay, now check. Is this formula 2kp cos theta by r cube and this formula the same thing? Yes. So this is another of the way in which you can find out the electric field due to a dipole. And this method will be very important in the upcoming problems. Understood? This kind of assumption that I'm doing out here. Okay. So in the previous question we have derived the electric field along this line would be kp sin theta by r cube, and along this line would be 2kp cos theta by r cube. In this question nothing separate is asked. They have only asked find the electric field due to the same dipole, okay, along this line or along this component and along this component. Okay, understood? In the previous question we have found out electric field along this line, that means perpendicular to the earth and along the earth. In this question they have asked find the electric field along the dipole, okay, along the dipole and perpendicular to the dipole. So you have to find out E perpendicular and E parallel, okay, or parallel to the dipole and perpendicular to the dipole. Okay, so we'll just, this is nothing but a concept of vectors, this has nothing to do with electrostatics. So if I take the first part of the question, electric field along this line, or E perpendicular is nothing but, see, component of this vector along this line plus component of this vector along this line. So if this is angle theta, okay, how much is this angle? This angle is also theta. Okay, this line and this line makes 90 degree. If this is theta, this is 90 minus theta. So 90 minus theta can be written as theta dash. Now this line and this line are 90 degree. Theta dash or 90 minus theta. So this angle would be theta. And this line and this line are also 90 degree. So if this is theta, this is 90 minus theta or theta dash. So E perpendicular is nothing but 2kp cos theta by r cube into cos theta dash. Cos theta dash. That means component of this vector along this line plus kp sin theta by r cube into cos theta, that means component of this vector along this line, isn't it? Which should be equals to, if I take, see, cos theta is nothing but cos 90 minus theta, and cos 90 minus theta is nothing but sin theta. So let me write out here sin theta. If I take kp by r cube common, kp by r cube is nothing but 2 cos theta sin theta plus sin theta cos theta. Now these two can be added, okay, so 2 cos theta sin theta plus cos theta sin theta is nothing but 3 cos theta sin theta. So this is nothing but 3 cos theta sin theta, 3 cos theta sin theta. Okay, now you can either leave the answer as this one, or what is sin theta cos theta? Sin theta is, cos theta is nothing but sin 2 theta divided by 2, isn't it? So this can be written as kp by r cube into 3 by 2 sin theta cos theta, or sin 2 theta, isn't it? Now I can rearrange this as electric field at perpendicular position is equals to 3 by 2 kp sin 2 theta by r cube, isn't it? So electric field is equals to at perpendicular position 3 by 2 kp sine 2 theta by r cube. Similarly, what is the electric field at this axis or this line? It is nothing but component of this vector along this line minus component of this vector along this line. So E parallel or electric field in parallel axis. Electric field in parallel axis is equals to 2 kp cos theta by r cube into how much is this much angle? Okay, how much is this much angle? If this is 90 minus theta, this line and this line makes 90 degree. So this line is nothing but theta. So 2 kp cos theta by r cube into cos theta minus kp sin theta by r cube into cos theta dash, cos theta dash or cos 90 minus theta. Cos 90 minus theta is nothing but sin theta. Sin theta. If I take kp by r cube common, it is nothing but kp by r cube 2 cos square theta 2 cos square theta minus sin square theta sin square theta. Fair and simple. Now you can either leave the answer as this one, or you already know that cos 2 theta is nothing but cos square theta minus sin square theta. Okay, so cos square theta minus cos 2 theta. Okay, just leave the answer as this one only. Okay, E parallel would be how much? Kp by r cube. E parallel is equals to kp by r cube 2 cos square theta 2 cos square theta minus sin square theta minus sin square theta. Okay, which is equals to, now if we add these two vectors, this parallel vector and perpendicular vector, would get the same answer as previous question. The total electric field is equals to kp by r cube under root of 1 plus cos cube theta. Okay, it is nothing but playing with vectors. Now see, the second part of the question is saying at which point is the electric field perpendicular to the P. Means if I draw the same diagram, okay, out here. So the question is saying the perpendicular component to P. That means electric field exists only in the perpendicular component. Okay, the parallel component becomes zero. So there is no parallel component of electric field. So I have to find out all the point in space such that there exists no parallel components of electric field. That means there is exists no component of electric field that is in this direction, isn't it? So I have to find some angle. See, if you see this equation out here, okay, that means what I have to do? I have to make this component of electric field is equals to zero, isn't it? Okay. So E parallel is equals to 0. And why I'm making E parallel is equals to 0? Because the question is asking at which points is the electric field due to this dipole perpendicular to this dipole. That means I have to find out all the point in space where the electric field is perpendicular to the dipole, or where the parallel component of electric field becomes 0. So E perpendicular is equals to E parallel is equals to Kp by R cube 2 cos square theta minus sin square theta should be equals to 0. So if I solve this equation, 2 cos square theta is equals to sin square theta. Sin square theta, I've taken this, I'm solving for this only. Or sin square theta by cos square theta. Or 2 is equals to tan square theta. Or tan theta is equals to root 2. Okay. So at values of tan theta is equals to root 2. So for values of theta is equals to tan inverse 2, okay, tan inverse root 2, the electric field would be perpendicular to the uh, dipole. So what I'm trying to say is, suppose this is the dipole, okay, when theta is equals to tan inverse root 2, so that means for a certain angle of theta at every point in this space, that means when tan theta is equals to some particular, let me erase just this one, when tan theta is equals to under root of root 2. So suppose I draw a line. amount here. Tan theta is equals to, I draw a cone out here. Okay, same cone I draw out here. This also is theta. So if tan theta or theta is equals to tan inverse root 2, that means at every point in this cone, okay, okay, this is a 3D cone, no? This is a 3D cone, okay. What I'm trying to say is at every point in this cone, the electric field would be perpendicular to the dipole. That means electric field will be in this direction. Electric field will be in this direction. Okay, there exists no parallel component of electric field at every point in this cone. Okay, understood? At the front of the cone, the electric field will be in this direction. At side, it will be in this direction. At right hand side, it will be in this direction. Understood? But there exists no component of electric field in upward direction or downward direction or parallel to the dipole. Okay, in this question, there is an external electric field out there. Okay, in not. And inside this external electric field, there is a dipole kept inside the external electric field along the direction of electric field. Fair and fine. Now, due to this external electric field and the electric field generated due to this dipole, okay, there is some other combination of total electric field generated, and of that total generated electric field, the equipotential surface is given in the form of a sphere. Okay, this is the equipotential surface of the total electric field generated by the combination of external electric field and electric field generated due to a dipole. The question is asking, we have to find out the radius of this sphere r. Okay, now see, if I draw this sphere outside, I'm just drawing this sphere outside. Okay, now due to the total electric field, okay, the equipotential surface generated is a spherical surface. Okay, what was the first thing that I said about potential lines and field lines? They always intersect each other at 90-degree angle. So if this is a potential surface, the total field would be perpendicular to the surface, isn't it? Perpendicular to the surface. The total electric field at each point would be perpendicular to the surface. Now, if I pick any one of the electric field line and analyze it, I'll get the gist idea of what the things look like, no, or what is the radius of the circle. So let's pick any one of the field lines. Let's pick these field lines. Okay, this field line. Now, if I extend this line, this was the field line. Okay, if I extend this line, this will meet at the center of the sphere. Let this be R, and at the center of the sphere, it is nothing but a dipole of dipole moment P is kept. Okay, and this total electric field is generated. This total electric field is generated due to a combination of external electric field plus electric field generated due to a dipole. Okay, let this angle be theta. Okay, now at radial position, this is point R, no? So perpendicular to the radius. Perpendicular to the radius means along the tangent of the sphere. In this direction, the electric field generated is nothing but Kp sine theta by r cube. I already did this in previous question. And along the component is nothing but, or along the radial component is nothing but 2 Kp cos theta by r cube. Okay, these two electric fields are generated due to this dipole. Now there is another electric field. The external electric field is in this direction. So the external electric field is in this direction, E naught. Now the total electric field is in radial direction. That means what? The tangential component of electric field will be zero, isn't it? That means the tangential component of E naught would cancel out this Kp sin theta by r cube. So if there are three vectors, first vector, 2 kp cos theta divided by r cube divided by r cube. This is nothing but r cube. Okay, r cube. This is generated by dipole. Okay, tangential to this or tangential to the sphere is nothing but kp sine theta by r cube. This is also generated by dipole. And the third vector is E naught. Okay, this is generated by external electric field. All I'm trying to say is the total electric field. That means the combination of vectors due to all these three electric field vectors is in this direction. That means what? The tangential component would get cancelled or the tangential component would be 0. Okay, so if this is angle theta, how much is this much angle? Theta only. So that means if this is angle theta, if this is angle theta, this angle is also theta, and tangential component is nothing but this one. Okay, if this angle is theta, this angle is 90 minus theta, so theta dash 90 minus theta. So can I say E naught cos theta dash is equals to kp sin theta by r cube? Because why? The tangential component of electric field out here is equals to 0. So kp sin theta by r cube is equals to E naught cos theta dash or cos 90 minus theta. Cos 90 minus theta is nothing but sin theta, isn't it? Okay, sin theta and sin theta would get cancelled. So r cube is equals to how much? Or r cube is equals to kp by E naught. Okay, or r is equals to kp by E naught to the power 1 by 3. Understood? The radius of the equipotential surface or radius of the equipotential sphere is nothing but kp by epsilon or kp by E naught 1 by 3. This is E naught or external electric field. Okay, kp by E naught 1 by 3. So this question will follow a similar kind of method that we have applied before. Okay, there are two wires, first wire and second wire. Okay, and these wires are in z direction. That means these are infinitely long wires in z direction. That means this wire is in the z direction. Okay, and this wire has plus lambda charge distribution, and the bottom wire or this wire has minus lambda charge distribution. Both the wires are in z direction. Okay, okay, we have to find out the potential and electric field out here. Okay, so first thing we'll find out with electric field is, suppose there is an infinitely long wire. Okay, what is the electric field at distance r? Electric field at distance r is nothing but E is equals to 2k lambda by r. We have done this kind of problems before, isn't it? So what is the potential or what is the electric field at this point? See, to find out the electric field at this point, we have to join this line, okay, and this line. Okay, the length of this line is nothing but, if this length is r or if the length of this much distance is r, this much length is nothing but r minus l by 2 cos theta. I have already done this before. And the bottom line is r plus l by 2 cos theta. That means this much length is nothing but r minus l by 2 cos theta, and this much length is nothing but r plus l by 2 cos theta. But this is l. Fair and fine. Now, if I observe properly, due to this positive charge, okay, the electric field would be in this direction, isn't it? Or along the line E due to plus lambda. Due to minus lambda or due to this wire, the electric field would be in this direction, E minus lambda. Okay. Now, because that we know this length L is much smaller than this distance R, isn't it? This length L is much smaller than this distance R. So, can I say that this angle is nearly equals to 0? Or the total electric field would be, or total electric field out here would be how much? Electric field due to plus lambda minus electric field due to minus lambda. Why? because I have considered this angle to be 0 and this electric field and this electric field are assumed to be whole. Understood? So this is the primary assumption we do out. Okay. Now what is the electric field due to the positive lambda charge? Or what is the electric field due to this infinitely long wire? 2k lambda by r, where r is nothing but L r minus L by 2 cos phi or cos theta. So 2k lambda by r minus L by 2 cos theta. This electric field is nothing but 2k lambda by this distance, but this distance is nothing but r plus L by 2 cos phi, r plus L by 2 cos phi. A total electric field at this point is nothing but 2k lambda r minus L by 2 cos phi or cos theta minus 2k lambda by r plus L by 2 cos theta. Okay. Now what we'll do? We'll take 2k lambda common out here. So we'll take 2k lambda common from both the term. Okay. 2k lambda. And what to do? We'll multiply the or we'll take common LCM. If I take LCM out here, this will get multiplied by this one, and on the numerator would obtain r plus L by 2 cos theta, r plus L by 2 cos theta minus r minus L by 2 cos theta, r minus L by 2 cos theta. Fair and fine. This r and this r would get cancelled. This is nothing but a minus b into a plus b, which is nothing but a square minus b square. So electric field is nothing but 2 into L by 2 cos theta. Why? Because this and this would get added, minus and minus becomes plus, and L by 2 cos theta plus L by 2 cos theta becomes 2L by 2 cos theta divided by r square minus L square by 4 cos square theta, a square minus b square into 2k lambda into 2k lambda. Now let's cancel out this 2 and 2. Okay, which is nothing but L cos theta by or L cos theta by L square by 4 or r square minus L square by 4 cos square theta. Now this value or r square by 4 cos square theta is very small when compared to the distance r. Okay, assuming r is much greater than L, what will happen? This term will tend to 0, isn't it? Or electric field at this point would be L cos theta by r square into 2k lambda. Now this much is done. Okay, so the electric field at this point is along the direction of r with the magnitude of 2k lambda L cos theta by r square. This much is fair and fine. Now how do I find out the potential at this point? See, what is the relation between electric field and potential? We do know that electric field or minus dV is equals to E dot dr, isn't it? I have already derived this before. It comes from negative of work done is equals to force into displacement. Okay, now minus dV, if I integrate this one, okay, or minus dV is equals to what is the value of E at point r? The value of E at point r is nothing but this value or 2k lambda L cos theta by r square. 2k lambda L cos theta by r square into dr. Now only r is variable out here, no? This r is variable out here. Everything else is a constant. So if I integrate this one, it is coming as minus v is equals to 2k lambda L cos theta r to the power minus 2 plus 1 divided by minus 2 plus 1. Okay, minus 2 plus 1 is nothing but minus 1. Okay, and out here in the numerator, minus 2 plus 1 is also nothing but minus 1. This minus, okay, would cancel out this minus. So this minus is cancelling out this minus. So what will I get? I'll get this value. Okay, and r to the power minus 1 can be written as 1 by r, or can be written as 1 by r. Fair and fine. So the potential equation of potential comes out to be v is equals to 2k lambda L cos theta into 1 by R. Now we have to put the limits out here. Okay. Okay. If I take this line, or if I see this line at infinity, at very far distance, what is the potential? Zero. So potential at infinity is equals to, at infinity potential is equals to 0. And as I come to this distance R, I have to find out the potential V at distance R. So V minus 0, which is equals to V is equals to 2k lambda cos theta 1 by R minus 1 by infinity, which is equals to 1 by R. So potential at this point is equals to V is equals to 2kl cos theta divided by R. Okay. So this was the solution to this problem. Now in this question, there is a positively charged ring and a negatively charged ring. Okay. They are separated by distance L. Okay. And this distance L is very small compared to X. We have to find out the potential and electric field out here. Okay. And we'll apply the same kind of logic we applied before. So this is, I'm just zooming out the distance L. So this is L by 2. Okay. This is L by 2. Okay. We have to find out the potential at distance X. Fair and fine. So let's take this point on midpoint between these two rings and let this distance be h. Okay, let this distance be h. So if I take this angle, okay, this length, and I have to take another length, how much? From the negative ring. Okay, now if I draw this line or join this line, and if I set this angle to be theta, okay, if I set this angle to be theta, we obtain the same kind of calculation, no? Okay, so this length would be nothing but h minus L by 2 cos theta, h minus L by 2 cos theta, and this length, the longer length, would be h plus L by 2 cos theta, isn't it? Okay, so potential at this point x, okay, would be nothing but potential due to positive ring minus potential due to negative ring, or plus potential due to minus q. See, out here this would come as negative because this ring has negative charge. This ring has negative charge. Okay. Now see, potential due to a positive ring at this point, at point X. Okay. From the point X is taken from the center of these two rings. Okay. And R is nothing but the radius of the ring. Okay. So potential due to positive ring is nothing but K Q pi. What is the distance? H minus L by 2 cos theta. So H minus L by 2 cos theta, and potential due to negative ring is nothing but K minus Q into H plus L by 2 cos theta. So it would be H plus L by 2 cos theta, isn't it? So the total potential out here, or V is equals to, if I subtract out here KQ by same kind of calculation, H minus L by 2 cos theta minus KQ, okay, H plus L by 2 cos theta. Okay, I have to take KQ common. If I take KQ common, it would go outside. 1 1 KQ. Then I have to subtract this term from this term. So I'm left with how much? 2L by 2 cos theta divided by h square minus L square by 4 cos square theta. Okay, I just haven't made the LCM. I just keep the LCM and the calculation. Okay, I've done this kind of calculation before also in the previous question. Okay, now we know that this term, or L, is very small compared to this X, or compared to this H. So this term will become 0. So we are left with potential is equals to this 2 and this 2 get cancelled. L cos theta divided by H square into KQ. Okay, our potential is equals to KQL cos theta divided by H square. Now I find out the potential. Okay, but I have to write this equation a little bit neatly. Little bit neatly means instead of term of h out here, I have to write in terms of x and r. Okay, what is the relation between h, x and r? Can I apply Pythagoras theorem? If I apply Pythagoras theorem, h square is equals to x square plus r square, isn't it? So if I apply Pythagoras theorem, h square is equals to x square plus r square. Okay, understood. Now see one more thing. If this angle is theta, this angle is also theta, isn't it? This angle is also theta. Why? Because these are parallel lines, isn't it? And what is cos theta? Cos theta is nothing but base by hypotenuse. Base is nothing but x. So cos theta would be nothing but x divided by what is the hypotenuse? Under root of x square plus r square. So under root of x square plus r square. Now, if I substitute those terms out here, potential at point x is equals to kql. What is the value of cos theta? X by under root of x square plus r square into h square. What is the value of h square? X square plus r square, isn't it? Now these two terms, x square plus r square to the power 1 into x square plus r square to the power half, is nothing but x square plus r square to the power 3 by 2. So these two terms will combine and form x square plus r square to the power 3 by x square plus r square to the power 3 by. Okay, and I'll get my answer as kqlx divided by x square plus r square to the power 3 by 2, isn't it? Now the second part of the question is I have to find out the electric field at point x. Okay, now we can either find out electric field by using the same method, or you can use minus dv is equals to e dot dr, isn't it? Work done is equals to, or minus of work done is equals to force into displacement. So we can use minus dv is equals to e dot dr, or work done is equals to force into displacement. Okay, so electric field, if I want to find out electric field is equals to minus dv by dr, isn't it? So if I differentiate this v with respect to r, okay, or with respect to distance, I'll get the electric field, or E is equals to minus, I have to differentiate this entire term with respect to which variable, r or x. See, r is nothing but the radius of the ring, x is nothing but the distance from the axis. So I have to differentiate with respect to x, as I go far, the potential decreases, okay, and the electric field also decreases. So I have to differentiate this entire term with respect to x. So d of kqlx divided by x square plus r square to the power 3 by 2, okay, divided by dx. One thing to remember out here, okay, when I'm differentiating with respect to x, okay, that means the direction of electric field vector would be along the direction of x. That means the direction of electric field when I differentiate this vector would be along this line, or along the unit vector of x axis, or along this line. Understood? Okay. Remember the partial differentiation. Whenever I have to differentiate the entire potential with respect to x, I have to put I cap, no? So same type of concept is happening out here. Okay, when I'm differentiating the entire potential with respect to dx, I'm getting the electric field in this direction. Okay, and does there other component of electric field exist? Okay, see, due to symmetry means due to this circular symmetry, this component of electric field will cancel out this component of electric field. Okay, so due to symmetry I can observe that there are no radial component of electric field, okay, only axial component of electric field. Understood this much? So when I differentiate this one, I'll get E is equals to, I'll write out here, okay, E is equals to how much? KQL is constant, I'll take them outside, okay, minus KQL d of x by x square plus r square to the power 3 by 2, okay, divided by dx. So I'll just differentiate this entire thing in the next page. Okay, now what I have to do is I have to differentiate this term. Okay, so just let me differentiate. Now what I did out here was x into 1 by x square plus x r square to the power 3 by 2. So first I took 1 by x square plus r square to the power 3 by 2 common and differentiated x, plus then I took x common and differentiate this entire denominator term. The differentiation of this entire denominator term would come somewhat like this. Okay, now see out here, these two, okay, and the, wait a minute, these two will get cancelled. Okay, x and x would become x square. So okay, 3 to the power minus 3 by 2, minus 3 by 2 minus 1 is nothing but minus 5 by 2, minus 5 by 2. Okay, so this would become minus 3x square. See, this entire thing would become minus 3x square, minus 3x square to the power x square plus r square to the power minus 5 by 2, and this plus and this minus would become minus out here. So I left with this much term. Okay, or if I write it neatly, electric field is equals to minus kql divided by 1 by x square plus r square to the power 3 by 2 minus 3x square by x square plus r square to the power minus 5 by 2, isn't it? Now in this term, this denominator and this denominator are different. So I can multiply x square plus r square in the numerator and the denominator. So if I multiply those things, okay, with this term, if I multiply x square plus r square divided by x square plus r square to the power 3 by 2 into x square plus r square, I can do that, no? I can do this thing because both these things will get cancelled to become 1. Now if I multiply this 3 to the power 2 or 3 by 2 plus 1, this is nothing but 5 by 2. So if I add this x square plus r square out here, it would become 5 by 2 minus 3x square. This term is nothing but x square plus r square to the power 5 by 2. Now you have the same denominator. For electric field is equals to minus kql. I can take the common LCM, x square plus r square minus 3x square divided by square plus r square to the power 5 by 2, isn't it? Or if I expand this, okay, this minus 3x square and plus x square becomes minus 2x square. So this is become minus 2x square. Okay, and if I multiply this minus with this one, it would become nothing but E is equals to kql 2x square minus r square divided by x square plus r square to the power 5 by 2. 5 by 2. Now the part of the question was saying plot the graphs of this potential and electric field also. So if I draw the potential out here, see, the equation of potential is given by this value, isn't it? And the equation of electric field is given by this equation. So if I just take this diagram, okay, I just take this diagram and rotate it. Now after rotating it, what I'll try to do is I'll try to draw the graph bit of electric field with respect to x. So this is x-axis. Okay, this out here is the x-axis. Okay, in y-axis, first I'll plot the potential. Potential at x is equals to 0. Okay, at x is equals to 0, we have the center of the two coils or two rings. Okay, so if you plot this graph or if you plot this graph will come somewhat to be like this. Okay, somewhat at x is equals to 0, at x is equals to minus. Okay, and now if I plot the graph of electric field, okay, the graph of electric field would be somewhat like this. And the pertinent question is, sir, how do you know? See, I plotted this in Desmos, a graphical software called Desmos. and this kind of graphs you're not required to learn. Okay, and this kind of setup is also called Hemlock's coil. Understood? So Hemlock's coil is basically two rings separated by distance L. So just memorize this graph or memorize this graph of potential and electric field. And these are not that much important, but still, okay, when you're preparing for advanced, memorize everything that you can. This is the graph of electric field. Okay.